So we just saw an example or learned how to calculate MN for a beam. You're going to do this quite a lot, so I thought it would be handy, or I didn't think, the book thought, and everybody thinks, it'd be handy if we derive an equation for this to make it go quicker. But to be honest, I actually do what I did in the last video. T equals C, solve for A, Z is D minus A over 2, and Mn is T times Z. But if you ever want to put it in a spreadsheet or do something like that, I'm going to derive an equation for you. So here we go. Okay, so I'm going to share my iPad again. Here we go. Let's see. Okay, so here we go. So what we're going to do is just derive an expression for Mn. And we're just going to redo what we did, but with variables instead of numbers. So remember that we start off with this strain diagram, 0, 0, 3 on the top. And depending on where the neutral axis is, this strain here should be greater than yield. And what happens if you put less and less steel, you need less and less compressive force in the concrete, and so you need less area, and so the neutral axis will move up. And you can see as this neutral axis moves up, if this point is fixed, so let's say this is the new neutral axis, what's going to happen as you make the neutral axis go up, the steel strain gets bigger. And so if you have less than the maximum amount of steel, the neutral axis will be high enough where that the steel strain will be greater than epsilon y, and we know that the stress in the steel, because it's yielded, will be Fy. Okay. So this is just what I said. Don't put too much steel if you have less than a balanced, and we achieve that by making the steel strain 0.005, are actually greater than or equal to 0.003 plus epsilon y, so it's definitely yielded. Okay, because it's yielded, the stress here is Fy. We went over this, the equivalent concrete stress, the real stress looks like this. But this rectangle here has the same centroid and area. So the stress is going to be 0.8 F prime C. And the area it's going to act on, it's constant, is going to act on a height of A, which is beta 1 times C, and the width of the beam, which is B. So we've not really talked about beta 1 in detail. So coincidentally, beta 1 is also 0.85 for concrete that's 4,000 PSI or less. So if you're over 4,000, you reduce it. And the way I remember it is for every 1,000 over 4,000, you subtract 0.5. So for example, 5,000 F prime C is 1,000 over 4,000. So you subtract 0.5. So 0.85 minus 0.5 is 0.80. If you had 6,000, that's 2,000 over 4,000. So it's 2 times 0.05. So subtract 0.1, it'll be 0.75. And if you have any other number, you're going to have to interpolate. Okay, so I want you to find an equation for Mn. Okay, so excuse me, blow my nose. So you could pause the video here and try and figure it out, or just keep watching and see the equation. So here we go. Okay, ready? C, the stress is 8.5 F prime C. The area is B times A. T, the stress is Fy because it's yielded times AS. Okay, C equal T, solve for A. So A equals Fy AS all divided by 0.85 F prime C times B. Okay, just put that on the other side in the denominator. Okay, Z is d minus a over 2. Remember, because that's a. Uh, uh, the, from the top to the steel is d. So between the two forces is d minus a over 2. Okay, so z is just d minus a over 2. FYAS 2, 0.85 f prime c times b, or d minus FYAS 2 times 0.85 is 1.7 f prime c b. Okay, and then finally mn is, I'm going to use t times z. Okay, t was FYAS times z, d minus FYAS all divided by 1.7 f prime cb. And there you go. That's an equation you can put into Excel for mn. But really, I find it easier just to do the numbers. But if you want an equation, you could use this. And what we're going to do is we're going to non-dimensionalize this equation, but that will be in the next lecture. Okay, so there you have it, an equation for mn that you could put into Excel, but we're going to make it even more convenient in the next lecture.